Hello and welcome to my report on the Week 8 reading. There was a lot to cover this week as we looked at an introduction to electric circuits, the concept of resistance, resistors in series and in parallel, covered an example of circuit analysis, the concepts of capacitance, and lastly, circuits which contain both resistors and capacitors. The majority of the topics which we covered this week were new to me. From previous physics classes in high school, I was familiar with some of the basic circuitry ideas, such as what it means for a circuit to be in series and in parallel, and this week we expanded on some of the concepts from earlier in the course, such as the use of the equation for conventional current to produce an equation for resistance. First, we were introduced to some new terminology and concepts. The first of these was that a direct current circuit exists in a state called steady state. This means that the circuit is constant in time. We also looked at the node rule, which states that in a steady state circuit, the amount of current going into a conductor is equal to the amount of current exiting the conductor. Later, we saw that this was expanded to the statement that the delta V of a round trip is zero, which is in line with the conservation of energy. We saw that in a steady-state circuit, the magnitude of the circuit's E field is constant, and in the direction of the conventional current. We also looked at EMF for the first time. EMF is the electromotive force, and is the input energy per unit charge for a non-electrical process. When the conventional current is not too large, EMF is equal to the electric potential difference of a circuit's battery and is measured in volts. Next, we looked at resistance and a lumped element circuit model. These models consist of power sources, components, and wires. We assume the electric potential of a wire to be zero in this model. We also established the loop rule, which is that the sum of the electric potentials in a loop is zero. Next, we looked at an equation for resistance. Resistance is the magnitude of electric potential divided by the conventional current. When resistance is constant, this equation is called Ohm's law. Resistance is also measured in a unit called ohms, which is equivalent to a volt per ampere. It is also here where we define conductivity to be the equation you see here, denoted by lowercase sigma. You can also alternatively use the inverse of conductivity times with delta L over A to be the resistance. Following this, we looked at resistors in series and in parallel. The main topic covered here was resistance equivalence. With n resistors in series, you could replace them all with a single resistor with an electric potential difference equivalent to the sum of the n resistors' electric potential difference. Rewriting this, with each electric potential difference as the product of conventional current and resistance, we can cancel the conventional current from every term as it is constant in a steady state circuit, and we are left with a single resistor with resistance equivalent to the sum of the resistances of the n resistors. We can perform a similar process with resistors in parallel, but instead of starting with the electric potential difference, we start with the conventional current at each resistor. By rewriting and cancelling, we are left with the sum of the inverse of each resistor's resistance being equal to the inverse of a single equivalent resistor's resistance. We then looked at capacitance. The main takeaway here was that electric field in a capacitor is constant and that capacitance is equal to the charge divided by the magnitude of the electric potential difference of the capacitor. Capacitance is measured in farads. In physical terms, a capacitor with a large capacitance is able to store more coulombs of charge per volt of potential difference. The equation for a parallel plate capacitor can be seen here. Lastly, we looked at circuits with both a resistor and a capacitor. We learned that these types of circuits are quasi-steady state, and their conventional current and charges are products of time. We can see each of those equations here. The other thing we learnt was that if you had a circuit with a battery, light bulb, and a capacitor, the light bulb would initially light but then dim over time and turn off. I think the hardest topic this week by far was these RC circuits. It took a while to understand what was actually going on, but even then I don't think I really got it until I read the physics book page on RC circuits. When I think about this topic in the context of my major, computer science, I'm most interested in capacitors and capacitor technology. Without these, we wouldn't have modern electronics in the same way at all. I'm particularly interested in researching what the current breakthroughs in capacitor technology are. Thank you very much for listening.